What we see in the sky is just the tip of the iceberg. The sun, moon, stars, planets, and galaxies. All of this visible universe makes up only 5% of its total composition. But what hides in the remaining 95%? Today, the vast majority of scientists believe that our universe is primarily composed of dark matter and dark energy. These are two forces that are invisible and intangible. However, without them, the universe itself might not be able to exist. One of these forces waters the universe, holding galaxies together and preventing them from falling apart. The other does the opposite. It stretches space itself, causing galaxies to move away from each other at an ever-increasing speed, sometimes even faster than the speed of light. But if these forces are invisible, how can we study them? In 2011, the European Space Agency decided to tackle this problem differently. Instead of searching for these forces directly, they study the traces these forces leave behind. If galaxies are clustered in one place, dark matter may be at play. If they are rapidly dispersing, it could be a sign of dark energy. To test this, the Euclid project was launched. It is a space telescope designed to create the most detailed three-dimensional map of the universe ever made. This map will help scientists understand how the two invisible forces of dark matter and dark energy have shaped the structure of the cosmos. In July 2023, the Euclid telescope was launched. Just recently, it sent back its first unique images of distant galaxies, nebulae, and superclusters. These structures seem to bear the imprint of these mysterious forces. These observations are particularly important right now. Recent data from scientists at Lawrence Berkeley National Laboratory points to strange behavior in dark energy. What if our universe is changing faster than we thought? Euclid is known as the cosmic detective because it is not just a space telescope capturing stunning images of deep space, but a genuine investigation into one of the biggest mysteries of the universe, the nature of dark energy and dark matter. As part of its mission, which continues until 2030, it will study 1.5 billion galaxies, peering into the most distant corners of the universe billions of light years away, and in doing so, uncover the true nature of these two mysterious forces. So far, the Euclid telescope has only explored 1,000% of its target. Between March 25th and April 8th, 2024, it captured 260 images of the southern sky, covering an area 500 times the size of the Moon as seen from Earth. From these images, scientists have created a mosaic containing millions of stars and galaxies. And this is just the beginning of its mission. Let's start with a picture of the most massive known structure in the observable universe. Scientists call this image a revolution in astronomy. It captures the Perseus cluster, with 1,000 galaxies belonging to it, and more than 100,000 additional galaxies in the background. Many of these faint galaxies have never been seen before. Some are so distant that their light has taken 10 billion years to reach us. This huge cluster, located 240 million light-years away, could not exist without dark matter. Scientists say the mass of the visible matter, stars, gas, and dust, is simply not enough to hold everything together through gravity. It is the invisible dark matter that acts as the glue, preventing the galaxies from flying apart. One of Euclid's key missions also includes studying how dark matter and dark energy affect the shape and motion of galaxies. These invisible forces directly influence the appearance of galaxies and their evolution over time. Dark matter acts like an invisible framework, attracting ordinary matter, stars, gas, and dust to help galaxies maintain their structure. You can think of it as a kind of gravitational glue that holds stars within a galaxy. Without this glue, everything would disperse into space. Therefore, the more dark matter, the denser and more stable the galaxy. Dark energy, on the other hand, operates on a much larger scale and has the complete opposite effect. It pushes galaxies apart, expanding the universe. It affects the speed at which galaxies move away from each other, the frequency of their collisions and mergers, and the conditions under which they continue to exist. These two forces, one pulling and one pushing, create the unique cosmic pattern of the universe, determining whether galaxies appear compact, scattered, or vast and dense. It is therefore no surprise that one of the first galaxies observed by Euclid was nicknamed the Hidden Galaxy, or Ghost Galaxy, IC 342. It is also considered a twin of our Milky Way, having the typical spiral shape of most galaxies. But galaxies were not always like this. In the early universe, most galaxies were small and irregular because they formed in a much hotter and denser cosmic environment, very different from what we see today. This made their formation process chaotic. The collapsing gas and dust under gravity could not gather uniformly, so the first generation of galaxies looked very different. They became the foundation and building blocks for larger, more ordered systems like modern spiral galaxies. Although such irregular galaxies are extremely rare today, they can still occasionally be found, even relatively close to us, like the galaxy named NGC 6822. It was the first irregularly shaped galaxy observed by Euclid, located just 1.6 million light-years from Earth and belonging to the same galaxy group as the Milky Way. The last time scientists had the chance to observe it was through images from the James Webb Space Telescope, but those photos cannot compare to the images captured by our cosmic detective. In these pictures, you can clearly see the vast difference in how Euclid surpasses its cosmic colleagues in object detail and color resolution. Thanks to its infrared instruments and wide field of view, scientists have already identified many globular clusters in this image, ancient star-forming structures held together by gravity, containing thousands of stars. It also highlights the most active regions of the cluster, the H2 regions, where stars are frequently born. These star clusters also exist in the Milky Way. Euclid captured a stunning image of a cluster named NGC 6397, located 7,800 light-years from Earth. Observing these structures in detail is extremely difficult because most stars are concentrated near the center and brighter stars obscure the fainter ones. NASA's Hubble Space Telescope managed to observe the core of NGC 6397 in detail, but observing the periphery with Hubble would take a very long time, whereas Euclid can do it in just 1 hour. In the same amount of time, Euclid captured the most detailed image to date of a vast star-forming region called the Horsehead Nebula. It is located south of Alnitak, the easternmost star in the famous belt of the Orion constellation, 1,375 light-years from Earth. Many telescopes have photographed the Horsehead Nebula, but none have captured it with the clarity and wide scope of Euclid. For example, the James Webb image only captured the very top of the nebula's head. Next to it is the Hubble image, which covers a slightly larger area. However, Euclid's image is breathtaking, showcasing the entire nebula in full, thanks to its detail and scale. In this region, scientists will use the data to search for dim and previously unseen planets with masses comparable to Jupiter in their cosmic infancy, as well as young brown dwarfs and newborn stars. These studies are valuable because everything born in this nebula was formed under extremely special conditions, shaped by the radiation from the very bright star Sigma Orionis, located above the Horsehead Nebula. This radiation strongly affects the gas and dust that form stars in the surroundings. In the photo, you can see how the light from Sigma Orionis makes the clouds behind the Horsehead Nebula glow, while the dense cloud that forms the horse's head itself blocks the light from behind, making it appear dark. The amazing capabilities of the Euclid telescope began to emerge as early as its first test run in September 2023, when it sent only a few images back to Earth. But in one of them, scientists saw something extraordinary, a perfect Einstein ring. This is a rare cosmic phenomenon that occurs when a massive object, like a galaxy, bends the light from a more distant galaxy behind it, forming a ring that captures the light. This effect is called strong gravitational lensing and helps scientists peer deeper into the universe. To understand why this is important, imagine a huge lens, but instead of glass, gravity is at work. The gravity of any massive object, such as a galaxy or a cluster of galaxies, distorts the space around it. Light passing through this distorted space bends, just as light passes through a magnifying glass. Thanks to this effect, we can see objects that would otherwise be hidden. Distant galaxies that are normally too faint become brighter and sometimes even appear larger. Occasionally, the gravitational lens is so precise that the light is bent into a perfect ring, as captured by Euclid. In this image, you can see how the galaxy NGC 6505, 590 million light-years from Earth, bends the light of another, more distant galaxy 4.42 billion light-years away. The gravity of NGC 6505 distorts the incoming light into an almost perfect ring surrounding the galaxy. In the most recent data received from Euclid, scientists have discovered 500 new gravitational lenses, where one galaxy bends and amplifies the light of another. It is expected that by the end of the mission in 2030, this number will exceed 100,000, which is 100 times what we currently know. Meanwhile, the 2,000 scientists from around the world participating in the Euclid project will analyze the data to unravel the universe's greatest mysteries, the nature of dark energy and dark matter. But even now, the findings on this invisible force have taken a rather unsettling turn. A team of scientists at Lawrence Berkeley National Laboratory has made a new discovery that could upend our understanding of the universe's future. Their research suggests that dark energy is beginning to become unstable and is losing its strength. The universe continues to expand, galaxies move away from each other, and space itself, like a stretched piece of fabric, keeps expanding. For a long time, scientists believed this expansion would never stop. One day, the stars will burn out, matter will dissipate, leaving a cold, empty cosmos, the so-called Big Freeze. Until recently, almost no one doubted this. After all, the dark energy stretching space itself seemed extremely powerful, so powerful that it appeared to bypass the familiar laws of physics. One of its core principles is that the farther away objects are, the faster the space between them expands. For example, the Virgo cluster, about 50 million light-years away from us, is receding at a speed of 745 meters per second. Meanwhile, the Coma cluster, nearly 6 times farther away, is receding at over 4,350 meters per second. The farther away they are, the faster they move. At a distance of about 14 to 15 billion light-years, the expansion of space exceeds the speed of light. Does this sound like a violation of the laws of physics? Don't jump to conclusions just yet. Nothing can move faster than the speed of light, but this only applies within space. If space itself is expanding, these rules do not apply. Imagine a football field. The ball is a beam of light, the goal is our Earth, and the field is space. The ball rolls towards the goal at the speed of light, just over 186,000 miles per second. But the field itself is stretching, and it's stretching faster than the ball is rolling. This means it will never reach the goal. The same is true for distant galaxies. Their distance from us is increasing faster than light can travel. They are simply disappearing beyond the horizon of the observable universe. This immense cosmic force seemed destined to lead to the cold death of the universe. But recent research suggests there may be a completely different outcome. Enter the Dark Energy Spectroscopic Instrument, DESI, a scientific instrument at Lawrence Berkeley National Laboratory equipped with 5,000 robotic fiber optic telescopes that study millions of galaxies every night. Thanks to its data, scientists have created the most detailed 3D map of the universe to date, covering 15 million galaxies and 11 billion years of cosmic history. On March 19, 2025, the DESI collaboration released findings showing that dark energy reached its peak strength when the universe was 9.6 billion years old, about 70% of its current age. Since then, its influence has gradually waned and is now about 10% less than at its peak. This means that while the expansion is still accelerating, dark energy is slowly letting its foot off the gas. If dark energy continues to weaken, something truly unexpected could happen. It could, over time, change from a positive force of accelerating expansion to a negative one. Its effects would reverse. The universe would begin to contract. Galaxies would start moving closer to each other. Space would collapse, and the universe would end in a big crunch, a mirror image of the Big Bang. If this data is confirmed, it would be one of the most significant discoveries in the history of science. It would suggest that dark energy is not a constant force, but something far more complex, possibly related to physical laws we do not yet understand. Current research is still insufficient to determine where the universe is headed. But one thing is clear, our usual view of its future has begun to change. As scientists try to predict the future of the universe, they are also delving deeper into its past. Not long ago, astronomers succeeded in capturing the infant stages of the universe, the very first moments after its birth. Using the Atacama Cosmology Telescope, scientists photographed what the universe looked like just 380,000 years after its existence, one of the earliest observable stages. It is impossible to go back any further in time. The reason is that after the Big Bang, the universe was filled with an extremely dense plasma, so dense that light could not pass through it for hundreds of thousands of years. That is why it is impossible to capture images from an earlier period. However, 380,000 years later, the expansion of the universe caused the plasma to dissipate, and the radiation from the hot gas began to travel through space. From that moment on, the universe became transparent, allowing scientists to see what it looked like in its infancy.